Hi, my name is Narges. I'm a PhD student at Penn State University, and my advisor is Professor Kandemir. My talk today is around performance evaluation of stateful workflows on serverless platforms. Just a quick background, what is serverless? It's a cloud service that allows customers to write their application and deploy their code and then leave the rest to the cloud platform to, first of all, manage running the application and second is scaling the application when the demand changes. And it only charges the user when the application is running and not when it's idle. So this serverless model is very attractive for special use cases when there is a small, short, stateless functions to run with low traffic and unpredictable workloads. Some example of these services are proposed initially by AWS Lambda functions and then Azure and Google Cloud functions and etc. So what is missing in this model? First of all, the general purpose applications often do not fit into the category I mentioned. For example, there is often long running functions or chain of functions, or there is sometimes a shared state to be used by several tasks. We can still implement these applications using serverless model, but breaking them down into smaller tasks which connect through the storage is kind of like adding to the latency. And it's even more slower because the communication and state management has to go through this very slow storages. It also provides a very limited options for consistency and managing the shared state because it basically depends on the lower level of storage and what the storage provides here. The new trend in serverless model is to go towards the stateful serverless platforms. Basically, this new model is adding another level between the storage, another layer between the storage and the compute, which is the state management layer. This layer basically manages the communication between functions or sending events from one function to trigger another function, or maybe in some cases managing the state, the shared state between different tasks. What are the characteristics of serverless model is desired to be kept in this stateful model? So first of all, is disaggregation. We still like to keep disaggregation of compute and storage because it allows different auto-scaling mechanism or different pricing model for storage and compute, which is attractive. Also, we want to keep the billing model as the same pay-as-you-use model because it's one of the attractive features of the serverless models. What are the challenges? The auto scaling is hard because now we have data, and when the data is involved, it's going to be more challenging to scale the compute. And also, how to keep the performance in a reasonable range is another challenge here. Next, I will look at some stateful serverless platform proposed by some vendors such as Amazon AWS and Microsoft Azure. The step functions are AWS solution to allow developing a stateful workflow. So several Lambda functions can be chained together through a state machine with some JSON-based language to define the workflow. The workflow would be triggering functions based on the order of the state machine, and the platform is responsible to manage triggering the function or passing data between two functions. Some flexibility on control flow is available. For example, parallel execution of functions or branching or map states. The platform will manage to transfer data from one function to another. In other words, keeping the state of the workflow or modify the state throughout the DAG execution. There are some limitation on the amount of data to be kept as an state or payload size between two functions too. So this kind of limits the ability of a state function, functions. Some data transfer to or from the storage is still required for some large data. The states and actions will be recorded in table and be recovered when a Lambda function is finished and want to continue the execution of the state machine. The price model is relying on the discrete number of state transition in a state machine. So basically, it could be a challenge for developer to decide how they want to break the workflow to optimize the price and at the same time to preserve this logical independence of these Lambda functions. AWS actually has this graphical rendering of state machines, which makes development and debugging throughout the development much easier. Microsoft Azure has proposed a durable extension as a solution to the demand for the stateful serverless applications. This solution includes two components. One would be the Azure Durable Entities, and the other is the Azure Durable Orchestration. The entities are proposing a class-like or an actor-like model with one private and reliable state. Once the Azure entities are triggered, they kind of like specify some operations to perform on the state, to use the state or modify the state of the entities. The operations are going to be running sequentially, so no need to worry about the race condition on a state. Two entities can talk to each other through asynchronous messaging to avoid deadlock. And the second component from Microsoft, the second durable component from Microsoft is the durable orchestrators. This is kind of like new and interesting proposal because it allows the developer to create this kind of like structured composition similar to declarative languages, but this time is through writing the code and use any kind of like familiar programming control flows like loops or parallel execution or sequential flows or some kind of like aggregating the tasks. So it's kind of very developer friendly model, and it's only to support the workflow of the code. The actual work should be actually happening inside the stateful activities or stateless activities or stateful entities that the orchestrators are calling um, from the orchestration. So how durable orchestrators are basically durable. So this is basically through recording the state of the workflow in some history tables, and on any kind of like event, this storied orchestrator is kind of replayed from the beginning. But the replay this time is kind of like talking to the history table to get to the current state of the code and continue from there. Uh, for example, if a function call is returned back, then the orchestrator is gonna start from the beginning, but this time is gonna pass calling the function again and just reusing the result. Netright is in our references, and it's kind of like a new execution model from Microsoft. It's kind of speeding up the workflow execution by committing the recovery logs into the high performance devices like SSDs. The pricing model is basically orchestrators are charged based on the execution of memory and CPU, similar to functions. But on top of that, the event mechanism is kind of like managed through the queue polling. The frequency of the queue polling is going to be adjusted to avoid charging the user for the idle functions. um, when the orchestrator is kind of like waiting for the actual work to be done in, let's say, activities, the orchestrator is kind of considered idle. So the user won't be charged for the orchestrators waiting for the function to be called. So that's something good about this model. In the next section, I will talk about some case studies we have implemented with both Azure Durable Entities and Orchestration and AWS Step Functions. The case study is a machine learning application. A practical machine learning training workflow includes several steps, starting with data preparation. The data preparation includes feature engineering steps such as encoding of the non-numerical data and scaling, that's making the scale of all numerical variables consistent. And then another step, which is often required with data set with a huge set of features, is to apply dimension reduction to reduce the space by preserving the maximum amount of information. Then after the data preparation steps, the next step would be to find the best model to fit the data set. So several models can be trained, and for each model, several compute-intensive steps such as hyperparameter tuning is required. And at the end, among the trained model, the best one needs to be selected as the winning model. At the same time, once the data preparation is done and some matrices are kind of ready and the models are trained for inference, the input data set needs to pass through the same steps. So for all matrices and models trained in a training step, we need to apply those on the input query to result the prediction. So in this workflow, we are basically talking about two DAGs, one for the training and one for inference. And then each are basically sharing the states in different steps. The training workflow modifies the state and find the best fit in each step. And the inference is using those objects or models to basically use it for prediction. We had several implementations for this case study. First of all, to compare the end-to-end latency, we had the Azure function and AWS Lambda implementation. These are single stateless functions, and they often show better latency, as we will see in the result, because they don't need to recover the computational context during application execution, as in stateful implementations. But the problem is that once the data set or the model size or number of parameters in the model increases, then one short-lived stateless function cannot run the whole application. So using the stateful workflow is unavoidable. The next implementation we had is the traditional DAG implementation, which is using queues to connect several functions. Basically, one function writes some data or result in the queue, which triggers the execution of another stateless function. And a chain of functions is kind of formed in this way. We implemented that using Azure queues. And the next set of implementation, we used the stateful components. We had implementation with Azure Orchestration, which implements the workflow, but for each of these, the functionalities is calling as an Azure function as an activity. So it's important to note that Azure Orchestration provides sub-orchestrations too. So for model training, which itself includes several parallel DAG, for each model, we use this, parallel sub-orchestrations. Similar to that, AWS Step Functions are used to implement the workflow, calling Lambda functions for each step. And then we had implementation with Azure entities. We leverage the entities to keep the training models or encoding objects, etc. And then later we used it for inference. Basically, each entity defines at least two operations, one for fitting the model, and the state of the entity is the model itself. And then the other operation is basically for using that model for inference. The first results I'm reporting here shows the end-to-end latency of running the application. First thing to note here is that the stateless functions are faster than the stateful implementation on the AWS, and the reason is that when rebuilding this computational context takes time in different functions, and then moving data between the functions is still adding to the end-to-end latency. The queue implementation reports the highest end-to-end latency, and it basically shows that we can rely on the stateful workflows and durable orchestrations to do the job faster, rather than manually connecting the functions with the queues. One other thing here is the tail latency reported for entities, which is often much higher than the other two stateful implementation. And one reason can be that the entities are sometimes running the same functionality slower than the stateless functions, probably because of managing the state's overhead. The next results on the left side, I showed the price of execution of running the workflow with the rate of 1 request per second over a month. The price comparison shows higher price for AWS implementation. The stateful price of AWS is very insignificant because it's basically just calculating the number of transitions and calculate the price based on that. For Azure implementation, it was the queue polling price that adds to the stateful latency, and looks like it's higher than AWS, although the stateful price in both cases is less than 10% of the total price. On the right side, I showed the end-to-end latency of the ML inference workflow. One thing to note here is the low latency of Azure durable implementations, which is probably because of the lower access latency to the trained objects. And the last result I want to show here in this case study is a cold start delay of different implementations. The question I'm answering here is basically which containers or components are taking more time to start the execution from the time that those functions are triggered. And my result shows that orchestrators are fastest to start and quite reliable in the start time. Entities are on the second rank. And then AWS Step Functions, those are also reliable, but always around like 3 seconds of delay to start. And the last one in the ranking, the top one in the graph, is basically these queues, which takes more time to transfer the flow from one function to another. The second case study I'm discussing today is a video processing application. The workflow is to receive the input video and breaks it into smaller chunks and then invoke many parallel workers to process the video, which is a face detection in this case, and then at the end merging the results to form the output. You can see that the AWS Step Function example here. One thing to note here is that we could not find an automatic way to change the number of workers, so we had to change it statically. We leveraged the map state to implement this application with AWS Step Functions. However, in Azure orchestration, this is basically just a for loop or a parallel task, which can accept any number as the input for the number of workers. So here you can see the end-to-end latency of processing a 100 megabyte sample video, and the model we use here is 1 megabyte, and each worker needs to fetch this model from the storage and use it to process its share of the video frames. We increase the number of workers, and the expectation is that the parallel portion of the code speeds up with more workers. So you know about the Amdahl law, and the sequential parts of the workflow, which is breaking and merging the video chunks, those stay the same. What we notice is that increasing number of workers help to reduce the end-to-end latency of AWS significantly, around 80% reduction, as you can see here. Um, we notice an unexpected behavior for Azure orchestration that extending the degree of parallelism does not help most of the time. So we saw an improvement in 40 workers, but the trend did not keep up with 80 workers. In order to understand this better in Azure orchestration, we looked at the breakdown of the delay for task workers. One reason is that sometimes the start time is actually the reason, as the container is not ready and it takes time that enough servers are showing up to serve these small requests, basically the workers that are doing the parallel video processing. The second reason is that sometimes the queue time was higher because most of the workers are scheduled on the same server and the waiting time is actually causing the delay. We collected the scheduling time of these workers among 50,000 workers. Almost half of the workers experienced like 40-second of delay to start the execution of this compute intensive part of the workload. And around 5% of the workers experience more than 4 to 5 minutes of delay. Overall, the tail latency of scheduling for all individual workers is around 12 minutes. And as we know, the tail at a scale is not tail anymore. Basically, when we need to wait for like, let's say 20 workers to complete the execution so we can go to the next step of the workflow, then the tail is actually becoming the median latency in this case. So as we saw in the previous graph, the median latency is around like 12 minutes for Azure orchestration, like here. We also estimated the monthly cost of both implementations and compared with a stateless implementation. For AWS functions, we had the flexibility to adjust the memory allocation for the execution instances, and we wanted to get to the same latency as Azure stateless functions. So we have a fair comparison. So we had to increase the memory allocation to 2 gigabyte to get the same latency. This actually caused the base price, which is the computation price for AWS, to go higher. The computation price is actually described in terms of GB seconds, which is basically a combination of memory and the CPU times of the work. On the other hand, the Azure transition cost, which is the green part, is around 80% higher than the AWS transition cost. And in this case, it doubles the price of the price that the customer has to pay for the stateless implementation in Azure. The AWS Step Functions, even though the number of state transition is very high in this case because we have a lot of workers, but it still is around like 5% of the total execution time. So the takeaway here is, first of all, to compare the programmability of these stateful platforms, we conclude that the Azure orchestrations are more powerful to design the general purpose applications, and AWS is actually more debuggable because of the whole graphical user interfaces providing to design the state machines for step functions. In terms of latency, overall for the large applications, it's better to use the stateful services proposed by either vendors because the latency is much better than the queue implementations. AWS allows adjusting the memory for the serverless instances, hence it kind of like help to reach lower latency for applications such as ML training. But for ML inference, we notice higher latency for AWS. On a scalability of the parallel workflows, we noticed a misbehavior from Azure orchestration, which does not allow parallel workers to speed up the application execution time. On the cost, we notice Azure cost for durability is often higher than the AWS state transition cost of the step functions, but the computation cost of Azure is often less than AWS functions. Thank you for listening to my presentation, and please forward all of your questions and feedbacks to the email that you see on the screen.